everyone. My name is Ambrus. I lead the computer vision team at TRI. And today I'm going to be talking about object-centric representations for manipulation. The talk is going to be structured into three different parts. A brief intro where I'll talk about who we are and the things that we're trying to do. And then we'll talk about two different methods and types of models that vary with respect to the kind of data that we're trying to learn from. And then I'll conclude. So a couple of words about our vision. Basically, our goal at TRI is to create new technologies that will enable Toyota products, existing products and future products, to improve the quality of life of people and also society as a whole. And TRI is structured in a few different divisions, and the vision team is part of the robotics division. And one particular goal in the robotics division is the creation of large behavior models for general robots, or LBMs, as we call them. And on this slide, I'm showing a few examples of the kind of capabilities that we would want these robots to have in the future. So you can see different examples, different types of dexterous manipulation, interacting with objects, deformables, and things like that. And more generally, the idea is that we would like to be able to ask a robot to do something, something unique and something cool, and the system then should just work. And getting to LBM requires significant work, and there are lots of different components and aspects of this. There's a research strategy, a hardware strategy, a simulation strategy, compute strategy, and so on. The thing that I want to talk about for a little bit is the data strategy. And one of the things we're thinking about in particular is the mix of data that we'll have to learn from to get to these kind of general systems. And we're considering many sources of data while training, and in particular, internet data at one end of the spectrum, which consists of language, images, videos, and so on. And then at the other end of the spectrum, we have robot data, which is basically demonstrations, robot actions, and then the robot doing things for particular tasks. And then at inference time, the system basically takes as input sensory data and a text description, and we output robot actions. And if we take a closer look, most probably this LBM model is going to consist of an action encoder, language encoder, and then that's going to be coupled with, a vision encoder, a language encoder, and that's going to be coupled with an action decoder to basically generate what the robot is supposed to do. And so in the vision team, we're of course in the business of training visual representations, and with understanding or the idea that we train a representation, then we plug it into a system, and the aim is to find the best representation so that we get zero-shot generalization eventually, or quick adaptation to as many downstream tasks as possible. That's kind of the goal. And there are many different ways of training these visual representations. And over the years, we focused on a few different aspects or key properties of these representations, which we think are important for enabling different downstream applications. And so I'm going to briefly talk about what these are, and then I'll focus on object-centric representations today. So first, understanding 3D structure is something that we think is very important. And the idea here is that, the robot takes as input some data, typically in the form of an image or RGB images. We encode these, and then we want to be able to decode the structure of the scene in metric units, ideally, so that the robot can interact with the scene. I think that's quite important. It's something that we spent quite a bit of time researching. A second property is being able to capture or understand motion, and motion is a rich signal for learning, particularly for humans, and it's integral to how the brain develops and how we learn to perceive and understand the world. It's also useful for ML models, and then for embodied agents. The idea of understanding static versus dynamic, object permanence, making predictions about the future, and so on. And third, object-centric representations. And this is what I'm going to focus on today. And we think that objects are a promising abstraction for factorizing reasoning and interaction, and object-centric representations basically allow us to use perceptual content or elevate perceptual content in a way in which we can use it for action and symbolic cognition. And modeling objects with high accuracy is also important for embodied agents that need to interact with these objects, and we hope to achieve some form of generalization where learning to do something on an object with a particular geometry should then transfer to similar objects that have similar properties. And very briefly about the way we do machine learning at TRI. So we believe that we need to do more in addition to just scaling data sets. We need to couple, or what we're trying to do is couple data with principles which we derive from core knowledge that we possess about the world. So, like the laws of physics, or cognitive principles like object permanence, principles derived from geometry like multi-view consistency and things like that. So we try to use these ideas in conjunction with data to learn more effectively, and that's what we call principle-centric ML. Okay, so I'm going to focus on object-centric representations, of course, for this workshop. And so, as I mentioned, the talk is going to capture two different types of models. The first one is going to be on learning from videos, and this is a crucial part of our data learning strategy. So there's a vast amount of videos available on the internet. The question that we ask ourselves is, if we learn from this data, is it going to transfer in any way to the embodied systems that we're trying to create? And so the question we want to answer is, what do ML models learn? And in particular, what do video transformers learn? And we focus on video transformers because they're the most capable models we have right now. And it turns out that there aren't really many different interpretability papers that look at understanding what happens inside video transformers. And so to answer this question, we proposed a new method, which we call VTCD, Understanding Video Transformers via Universal Concept Discovery. And this work was led by Matthew Cowell, who is right here, and is a PhD student at York University. And this is a very, very high-level overview of the three different steps involved in this method: concept discovery, concept importance, and concept analysis. And this is also a paper that we present as a highlight in this conference, and Matt is going to present it in a poster later today, right after this talk. Okay, so we're going to briefly go through the different steps involved in this method and try to get an understanding for how this works and what these models learn. So concept discovery. We first take a set of videos, we pass them through a vision transformer, and we obtain a set of intermediate representations, which we then cluster using SLIC, which we found to work better than other methods, and we obtain tubelets. We repeat this process for several videos in the dataset, and we obtain a dataset of tubelets, which we then cluster, and these form the resulting concepts in the model. Once we have concepts, the next step is ranking them. We want to be able to say this particular concept corresponds to this part in the image or in the video, and this is how it affects model performance for a particular task. And this is the second part of the method, which looks at quantifying concept importance. And the way we do this is we first repeat the concept discovery process for all the heads in the model and all the different layers. And then we perform Monte Carlo sampling, and we randomly mask out many heads in the model, and we compute the drop in performance for whatever task the model was trained for originally. And then finally, after we do this for a few rounds, a few iterations, the final concept importance is the average drop in performance over a few of these masks. And this is a very high-level bird's eye view. We tried a few different methods. It was very difficult to remove concepts from the model and correlate that to performance changes. And finally, this is the method that worked quite well for us. So at this step, we have identified a set of concepts. We know what they detect in images. I'm going to show lots of examples of that. And we know how to correlate them to performance. So the next thing we looked at is what are these concepts and what do they relate to for different models? And so we tried to identify the most important concepts. We looked at the segmentation TCAL model, which is trained to detect occluded objects, or to track occluded objects on Kubrick. And we basically found that the most important concept is at layer 5, and it tracks the target object as well as similar objects around it that have similar appearance. And so we concluded that the model the most important thing the model learns is how to identify possible distractors so that it can disambiguate the target object. The second most important concept we found at layer 9, and it tracks the target object throughout the video. We also looked at a different video transformer model. We looked at the supervised video MAE model, which is trained for action recognition. And this is trained on the something v2 dataset for the class of dropping something into something else. We found the most important concept at layer 11. It basically captures the object being dropped until the drop occurs. And then it captures the object in the container. The second most important concept for this model is at layer 8. It captures the container without the object. So you can see how they relate to what the model is trained to do. Next, we looked at the third most important concept, and we found that it's similar across the models. It's a temporally invariant concept, and it's found earlier in the model in an earlier level, in an earlier layer 3 and 4, respectively. And so this led us to conclude that, first of all, positional information processing occurs earlier. And second, we found it interesting that these models share these concepts, and we asked ourselves the question, are there other concepts which are shared by these models? And if we were to expand this analysis to a larger set of models, are there concepts which are universal across video transformer models that are sort of independent of the downstream tasks that these models are optimized for? And we basically took inspiration from this Rosetta Neurons paper, which was recently published, and we tried to discover these Rosetta concepts. So I'm going to give you a very quick overview of how this works. We basically looked at 4 different models: TCAO, which we talked about, video MAE, self-supervised video MAE, and intent video, which is video language. And we looked at the IOU of the tubelets for a particular concept. And if that IOU is above a certain delta threshold, then we consider that concept to be universal across these 4 models. We also looked at subset overlaps, so for 3 models and for 2 models, and we tried to find these universal concepts. And we actually found quite some interesting things. So here is an example of a concept that captures rolling objects in all of these videos, so it's universal across. And we also found similarities in early layers across the models. So these spatially and temporally invariant position concepts. We found object-centric concepts in middle layers, so rolling objects, hands, and then in deeper layers, we found more complex spatio-temporal object-centric objects that capture objects before or containers before dropping events. So the very interesting part of this is that none of these models were really trained with any supervision for these kind of concepts or these kind of object-centric traits, and nevertheless they emerge from the data, even though the models are trained in very different ways. So you can find more info about this on the website, or from the archive page, or later at the conference, or today at the poster session. Okay, so the conclusion, which we found quite interesting and reassuring, is that spatial-temporal object-centric representations emerge in all of these transformer models which we studied, which are trained on video data. And this is important for us because for the LBM goal that we have, we basically want to train on a large amount of video data. And so object-centricness is important for these embodied downstream applications. Okay, so now we're going to change gears slightly and switch to a more sort of 3D focus, computer vision focus. And we'll look at learning from 3D data. And particularly the question that we ask ourselves is how can we use 3D object-centric models for embodied applications? And what I'm going to focus here is a series of papers from our team that reasons about 3D objects explicitly. So their geometry and the pose and the way robots can interact with them. And for robots to be able to interact with these, of course, we have to be able to locate them in the scene. So we have to be able to say, there's an object over here, this is its geometry, and this is its pose, so that we can grasp it and we can interact with it. And the challenge here is basically estimating the pose and the shape for these objects. And we want to be able to do this for any object, anywhere, and with an additional constraint that we should be able to do this from partial information, ideally from a single camera image. And the challenge here comes from the fact that generally the pose of an object cannot be fully specified without a priori knowledge of the shape and vice versa. And so therefore we need to reason about this joint probability of pose and shape given an observation, and sampling from this probability conditioned on partial information is very challenging because of the large multimodal space of possible solutions. And this becomes even more challenging in the zero-shot setting, where we basically want to do this for any object of any category in the wild, in any kind of domain. So I'm going to talk about a series of methods that basically tackle this problem with increasing levels of complexity, depending on the number of categories and the type of objects we want to be able to capture. So first, I'm going to very quickly, briefly talk about representing 3D objects with neural networks. Leaving pose aside, this is just 3D object representations. And basically what we want to do is we want to be able to represent objects as latent vectors in some kind of latent space. And we start from a set of meshes typically. We want to be able to encode these with a neural network, project them into a latent space. Each object should be represented by one vector in that latent space, Z. And we want to reach something like this, which is basically a latent space that captures these cars. It's represented as a sphere. It's nice and smooth. And as we move to different points in the sphere, we decode the latent vector into the corresponding shape. Here's another example from a more recent paper called Chapeau, where we did something similar for indoor objects. And the limitation of most of these methods is that you can basically represent multiple shapes, but you miss high frequency geometric details because they're globally conditioned. You have one latent, and then you're trying to represent the whole geometry from that with an MLP typically. So I'm going to very briefly advertise a recent work from our team where we basically looked at representing thousands or tens of thousands of objects with a single neural network. We wanted this to be efficient at compressing the data and still be able to capture high frequency details and different modalities. We wanted to be able to capture sparse and continuous signals, so we can encode SDFs, colors, and radiance as well. And so we're going to present this in a few weeks in SIGGRAPH. This is led by Sergei Zakharov from my team. And we're going to release one model for every sort of common or typically used data set in robotics. And then we hope to be able to just start from these as opposed to having to download these data sets. So with this method, we achieve 99.8% compression compared to the input meshes. So we'd have a model on the bottom right trained on Objaverse Elvis, which is 10,000 objects. The original data set with meshes and textures is 360 gigabytes, and our network is somewhere around 302 megabytes. So that's quite a bit less. And typically for smaller data sets, not yet for Elvis, we get around 98% reconstruction accuracy when we compare chamfer distance. So that's quite nice. Okay, so moving on, as I mentioned, is a research scientist in my team. It was when he was an intern with us and he was a PhD student at Georgia Tech. And so we basically, what we do is we first construct one of these latent spaces of objects, like I mentioned earlier. In this case, with disentangled shape and appearance, many technical details I'll skip over. We basically end up with a latent space that can be projected into 2 dimensions. The nice thing is that classes, objects, instances of the same class cluster together, which is what we want to achieve. We also recently presented an extension of this method called FSD in ICRA, where we basically try to do the same thing, but only from simulation data and then use self-supervision in the real data. So let's look at how this method works for finding and reconstructing objects, unknown instances of known categories. We basically take as input an RGBD observation, we pass it through a network, we get a set of heat maps, and then from these heat maps, we basically predict everything that we care about. So it's a typical kind of deep learning supervised pipeline. We have an output for the latent vector for the shape, from which we can decode the shape. We have an output for the texture. We have an output for the scale, rotation, and translation of the object. And for the mask, which is important if we want to do test time optimization, because with these methods, we can basically backprop from the observation, the camera image, all the way to the latent vector, and we can optimize the shape further and the pose and so on. So to give you a high-level summary of this method, we can basically regress full 6D pose, shape, and appearance. And we can do test time optimization to further improve these quantities. But this method has 2 main limitations. First, we output a single hypothesis. So we have one, for each object, we have one set of predictions. And this is going to be a problem for a set of objects that are symmetric, because then from partial observations, multiple possible poses are equally feasible, given the partial observation that we have. This is also going to be challenging when we move to more categories that we want to handle, particularly in the wild data sets, where canonicalization is not straightforward. I'm going to talk a little bit more about why canonicalization is important for these methods. And finally, another limitation is that this method is category level, meaning we deal with a set of known categories. And this was, a few years ago, we only had methods that could handle known instances. Then we had methods that can handle known categories, unknown instances, which was a big deal. But today we would want to really have methods that can handle any object in any scene. Let's also look at some results, which we see on this picture. So given an RGBD frame, we can get these kind of reconstructions. So the objects are placed in the scene, we know their geometry, we know their colors, and then we can use off-the-shelf grasp planners to figure out how to interact with them with the robot. And the code is available online. So the challenges which are inherent in modeling ambiguous poses are particularly apparent when we deal with symmetric objects, where we have a set of poses that appear to be equally feasible when we have just partial information. And so as we saw with Chapeau, most current methods regress a single pose, and then we have to use either data labeling or some kind of test time heuristic to basically figure out, to deal with these ambiguities and symmetries, which leads to instabilities due to the fact that the pose is inherently multimodal in some situations. And so to get around this issue, we designed a method, diffusion NOx, which we just recently put on arXiv, which handles symmetries and uncertainties by design or by definition. And we're interested in handling a large number of objects, again, from known categories. And we want to generalize to any real world domain. So we also release a generalization benchmark as part of this paper. So I'm going to just very briefly go through the different steps. We take as input an RGBD observation. We pass it through SAM. We get a mask for the object that we want to be able to identify and for which we want to estimate the pose. We take the corresponding depth. We also use Dino V2 features because they're very expressive at this, and we want to disambiguate between a large number of objects. And the way we solve pose estimation in this case is we use the diffusion model. There are some very nice properties that I'll talk about. We condition the diffusion model on a few different modalities. We have played all of this in the paper. And then we output what NOx, which stands for normalized object coordinate space. And I'll define that in the next in the next slide. And from Knox, we can basically regress the pose. For conditioning, we looked at the RGB information, the Dyno V2 features. We also have a class ID for the object. And finally, we found the depth to be quite important for disambiguation. Sorry. Okay, thank you. Better?
Yeah.
Okay. Zoom and being muted. Okay, so right, we train in sim. We make one important assumption, which is for these categories, we assume that they're all canonicalized, meaning instances of objects from these categories all have their frames of references aligned in the same kind of way, which is a fair assumption when we deal with curated data sets and small sets of categories. Normalized object coordinate spaces. This is an awesome image from the original paper by Wang et al. From 2019. We use basically their formulation. Each object is assumed to be in a unit cube, and basically the Knox map, which you see on the bottom left over there, is the projection of the observed surface of the object into the camera frame. So what we end up with is an image-like quantity that encodes in its channels the 3D coordinates of the objects that correspond to that particular, of the 3D point that corresponds to that particular pixel. So it's very useful because given a predicted Knox map, we have an initial estimate of the shape because there's a correspondence between the 2D and the 3D points. And we can also use off-the-shelf tools to basically estimate the pose, like PNP if we have just images, or point cloud registration if we have depth maps as well. Okay, so finally, once we estimate a Knox map, we use point cloud registration from the teaser++ method, and we align the predicted shape with the depth. This also gives us a measure of uncertainty, which is very nice and useful. So diffusion Knox can basically estimate multiple poses by design from different input noises, and importantly, even when conditioned on the same information. So we start from a set of conditioning variables, the RGB, the features, and the normals. We vary the noise, and then we get different estimates of the pose because the method is designed to capture this multimodality. And at test time, we can do this in a batch. We sample multiple noise levels, and we get different outputs of the pose. And because we have the confidence, we can select the highest confidence pose. Or if there are multiple poses that are high confidence, we can select the one which basically has the best kinematic constraints. So if in some cases the arm goes like this, it might bump into something, so we select the other pose, which actually made the results very, it improves the results quite a bit. And we have ablations on this in the paper. There's another nice example which shows how our method handles these symmetries. We basically show in the image 20 different poses generated from 20 different noises, and the unit spheres show the corresponding 20 rotations. And what we see is for the ball, which is an axis symmetric object, the poses are distributed around the axis of symmetry, which is great. For the cup on the far side, we see the handle, and that helps to reduce the set of possible poses to roughly one unique configuration, which is also nice to see because it validates that the method works. And then we have a cup that's closed where we kind of see the handle, but not really. And then we have poses that are distributed in a set of configurations that make sense given that observation. Okay, so to summarize, we can handle symmetries, uncertainties. We trained in sim. We checked generalization to the real world, and I'll show some results. This is basically a robot that's picking up these symmetric objects where methods struggle because of this ambiguity. These are images from this data set that we created, where we basically benchmark generalization. And it's basically the same instances of the same categories in challenging real world situations. A couple of limitations. Again, we're only category level, so we want to be more general. We don't do shape completion over here. So in some cases, that's useful if you want to know, have an idea what's behind what's visible, to be able to calculate a grasp that takes that into account. And we assume canonicalization, which is available for curated data sets, but it can't really be enforced in the wild. The other thing I want to mention briefly is that the code is available, and so it should be easy to use. And very briefly, I'm going to mention a recent paper that is currently under review. It's called OmniShape. And what we're doing here is we're basically expanding the generality of our method to jointly reason about shape and pose for any object. And we also want to be able to do this from partial observations like before, and particularly from a single RGB image if possible. And we can actually run most of the pipeline from just an image. We need the depth for scaling the resulting pose. And as I mentioned, canonicalization is an issue that we have when we go to broader sets of categories, and I want to talk a bit more about that. This is an image from the ShapeNet data set, 3 different classes, and they're rendered from the same viewpoint. And we see that they're aligned. The cars all face in one direction, the chairs face in one direction, planes face in one direction. And so that's nice because then we can train a pose estimator that is consistent, because all of the instances of the same category have the same consistent orientation. Now, what happens when we go to Objaverse, which is much larger data set, lots of shapes, lots of categories, is it's not curated. There's no canonicalization, so we can't train a method that outputs a single shape. It's much more difficult. So to handle this, we propose OmniShape, where we basically disentangle the shape and pose estimation problem into 2 different distinct probabilities. And we can reason about the joint probability by looking at these 2 distinct probabilities, and we can sample from the first one. We get a set of hypotheses, and then we pass those to the second method, and we get another set of hypotheses. So the method is designed to be multi-hypothesis by default. So I'm going to very briefly talk about how this works, the different components. We follow the same recipe as in diffusion Knox, and we use diffusion to regress normalized object coordinates for the visible object points in the image. The main difference here with respect to diffusion Knox is that we do this for a broader set of categories. So now we don't have canonicalization. We're operating on more in the wild kind of setting, and so we call the resulting quantity North for normalized object reference frame, mostly to disambiguate from the Knox quantity, which assumes canonicalization. And here are some results of the multi-hypothesis capabilities of our method. We can basically see that from an input image, we can generate a number of plausible north maps with different orientations, because the data set basically lacks this canonicalization, and so we capture this multimodality. A second observation is that the normalized canonical map gives an estimate of first estimate or a rough estimate of the shape, and we can use that to condition a shape prior. And so what we do is we combine this with an object-centric representation. In this case, we used triplanes, and you see here triplane representation and then the corresponding decoding object. We found that triplanes work very well when it comes to training them on a very large data set. And the other nice property is that basically they have 3 channels. So they plug very naturally into diffusion methods trained on images. And of course, we wanted to use one of those and see if we can adapt it to these kind of tasks. So basically, we take the partial point cloud, we plug it to a diffusion network where we complete the shape, and we get completed shapes. Let's look at some results. So we see the multi-hypothesis aspect of the method. We basically can generate many different initial shapes and poses, and then we complete these with the second stage of our network. We've done this for many different categories, and including some experiments with data that we collected ourselves. It's also worth noting that not all predictions are equally good, as you can see on this image, but usually from a large enough set of predictions, we have at least one that is quite good in terms of capturing the geometry or completing the geometry of the object. So to conclude this section and this method, with OmniShape, we can reason about both the pose and the shape in a factorized way. We can sample from both these distributions. This ongoing work, we have a couple of things that we're still working on. We don't have a scoring function, so we have lots of different solutions, but we can't automatically choose the best one. If we iterate through all of them, a few of them are going to be very good. So we're working on that. We're also working on representing colors. And here you see more results of how our method works on objects in the wild. So this solves the pose and the shape problem jointly, and we get, using depth just for scaling the pose, we can place the objects in the scene. These are examples of this method running on images that we collected ourselves with our phones. They're a bit cherry-picked, but they look very good. There are some that, but generally, if you sample enough completions, you are going to get something good. Okay. So with that, I come to the end of my presentation in the 3 sections. We basically talked briefly in the beginning about this large behavior model, which is what we're trying to achieve in the robotics division. We want to be able to learn from different kinds of data, which means being able to adapt to different modalities and deal with them. We saw that when we train on videos, we get these object-centric representations. They emerge without that sort of direct supervision, which is very nice. We briefly looked at modeling objects in 3D and with colors, and we can do this accurately, compactly, and in a differentiable way. And we are making progress towards zero-shot pose and shape estimation in the wild, which is crucial for interacting with objects. And I would also like to thank my many collaborators and to end here with questions. Thank you.
Thank you very much for the insightful talk. Any questions? Yes.
When you were talking about concepts, did you observe disentanglement in the learned concepts?
So depending on the, there's a great amount of overlap also, I think, in the concepts. And I think when we clustered the representations in the beginning, we went through a few different iterations. We went with Slick because it gave us more continuous concepts, tubelets through the video, as opposed to other methods that were kind of a bit more separated. Yeah, but there are many different concepts, and by correlating their importance with model performance, we were able to find the ones that affect the model the most. And also, it was interesting to see that they actually corresponded to the things which the model should be learning in an intuitive way.
How interpretable were the least important concepts or less important ones?
Maybe I'll let Matt answer the question.
A range. Some were like clearly colors or something at layer 1, and then others were kind of hard to see, might have been like a bit desperate across the video and were hard to interpret. Because you get about 1,000 concepts in your average transformer, so there's quite a number.
It was also nice to see that, early layers capture simpler things, and then we move and add in complexity as we go, object-centric, and then spatial temporal constraints and correlations and things like that as you build more knowledge through the transformer.
Other questions? Yes.
Hi, thanks for the talk. What are your thoughts on the use of like tactile information to make these same like pose and shape and object-centric representation?
Yeah, that's a very good question. And actually, we have some projects where we're doing that. You know, like diffusion knocks, we condition on a few input channels. We have a project where we're basically adding another input channel, which is a tactile map. And yeah, that works.
Is it harder to collect that tactile data than you just get this visual?
It is, yeah. I mean, of course, you have you know, like way more visual data because cameras are sort of ubiquitous. We have something called a bubble sensor. It's part of the Punyo project at TRI. It's an open source project. It's a soft sensor, and the goal is to basically build something like Baymax, you know, like a big robot that has these soft sensors everywhere. And these are, you know, you can press them and they deform when you interact with the surface. And so I think, and there's others, you know, there's gel sight and things like that. I think they're becoming more popular and more accurate. They're definitely not as widespread as visual information.
I also want to ask one.
There is a one, two.
I'm polite as a host.
To go back to the learning concept, did you find any relationship between the attention masks, the learned attention similarities, and actual concept relations that were happening? Like, so the attention mechanism itself, was it actually attending to different objects, or is it just the two bubbles?
Yeah, I think we went through a few different iterations in trying to figure out how to. Yeah, how to basically quantify the importance and what you know, how to mask different things. Finally, we went with CNMF, I think, for the clustering of the tubelets into concepts because that worked the best. It was very difficult to mask out just different parts of, you know, one head to zero out because it turned out that the transformer has many different ways of propagating information, and so most of the other things we tried, and Matt is going to talk more about this at the poster, actually didn't really work very well.
Yeah. You put me on the spot.
Okay.
I'm just kidding. So I think it was in diffusion knocks, or anyway, any of the other papers you presented.
Yeah.
Like you said, for instance, that it's not instance specific, but more like category specific.
Yeah.
But like you know, like for me, it should be even open world if possible. So how well or how hard would it be to generalize to open worlds? Like if I give it like an object that looks like a mug, will it be able to handle it like a mug, or it has to be retrained from scratch?
Yeah, so we do handle mugs over there, and it's because we have a data set, let's say, of 100 mugs. They have different geometries, but the handle is always in the same orientation. Let's say along the x-axis. So you see a mug, and you know that the handle is going to be in that direction. And so what happens when you move to Objaverse is you have 1,000 mugs, but then the handle isn't in that direction anymore. Once it's here and once it's there. And so then we needed to come up with something like diffusion knocks to be able to output, you know, multiple hypotheses and then sample from that and choose the best one based on registration. And with OmniShape, we went beyond that to handle any kind of object. So there we're relaxing this notion of category or this limitation.
Right. Okay. Thanks. Thanks again.
Thank you.